Hey everyone, I'm going to split chapter 7.6 into 3 shorter videos since we're really talking about 3 separate types of math. Well, they're not 3 separate types of math, but they're 3 different models that we're looking at. So if we look at what are we supposed to learn, we are talking about graphing exponential functions using exponential models. Then we are talking about graphing logarithmic functions and then using logarithmic models. And then finally, we are talking about graphing quadratic functions and graphing quadratic models. And then kind of an overall, how do you tell which one to use? And we'll talk about that in class. So none of these should be unfamiliar to you, but it may take a minute to kind of remember the differences. So exponential functions and quadratic functions should really be fresh in your mind right now. I'm going to skip this kind of first paragraph here because we've been looking at them since the start of COVID, okay? Let me get to the top of the page here, right? The exponential curves, we talk about that for the beginning of kind of the infection rate, like one person, each person can infect 2 other people or whatever that R naught value is. The R naught was the infectious rate, which is how many people you would be infecting if you had COVID, okay? And then we talk about, and actually short term, this is exponential, but while I'm thinking about it, long term, the infection rate becomes logarithmic, which looks a little bit more like this instead of going straight up. And the reason why is that eventually you're going to run out of people to infect. Like say it just runs its course and infects everybody in the United States. Well, it has to stop, or everybody in the United States, everybody in the world. It has to stop eventually when there's no more people to infect, right? So it would eventually level off at about 7.2 billion. Is that how many people are in the world right now? But short term, it's very exponential, right? And then when we talk about this curve here, that this is the one that everybody wants to flatten, right? And that's kind of the quadratic curve. So we know that we are going to go up and up and up and up and up until we can get control of it, and then it's going to come back down. So some pretty interesting real life situations happening right now that we can think about as we're going through all of these different models of data, right? And math, the reason math is so important, and maybe not to your everyday life, but so important that some people like math and eventually go in to do these things as their job and their career, is so that we can get models like this. Math predicts the future, right? So that's the most important thing about math, is it can predict the future for anything, literally anything, okay? So we're talking about exponential models, and let's just kind of go through. If memory serves, you guys, we have these kind of, we've always had these formulas, and I think the exponential model is a times 1 plus r to the power of x, right? And in here, the r is our rate, right? So we are either increasing or decreasing at a specific rate or multiplier, okay? And if it's not a rate, you can just have a number there. That's the difference between like a multiplier and a rate. And A, I'm not sure what they use. Oh, they use B. Maybe I should use B too then. The book uses B. B is going to be our starting value. Okay. So we're looking at this model. It's giving us here. And oh, they gave us a linear model. That was just part of that original first paragraph here. Now we're dealing with, here are those 2, what we were just talking about, where B is your starting point. but we don't really have the, or b is the multiplier, but it really doesn't have the starting point there. So I think the way we've learned it in our high school math is a little bit easier and better to think about, especially we'll be getting into interest rate problems in the next chapter. So graphing an exponential function, you can, sorry guys, you can either, I don't know why I'm sneezing so much. You can either do what it's saying and plot these points, which is the same as we would any points. You have your input for your x, and if we're graphing 2 to the power of x, you input that particular number or value, -3, you put it into the function and your output is 1/8. So if you input -3, your output is 1/8. And you can make this little table and you can graph it. I am okay with you guys, if you need to graph one, using either your graphing calculator or Desmos. So if you have your graphing calculator and you go to y equals, we'll clear out what I have in here. I'm going to put 2, and then your caret is the power of x. Okay. And then I'm just going to do a zoom standard, a zoom 6. And there it is. And you can also, if you do second and then table, you can also see all those points up. And the first one we entered was -3. Okay. All right. 0.125 is the same as 1/8. So here we have graphed it. Let's go back and see what they want to do with this. Oh, that's all. They just want you to be able to graph 3 to the power of x. I will say something interesting. When you're looking at your y-intercept here, it's at 1. So if we input 0 for x, our output is 1. And this is interesting because this means if we input, we have 2 to the power of 0. And I just want you guys to remember that any number to the power of 0 is 1. Okay, so any exponential function that only has a number to a power without any like plus this and minus this, that y-intercept or that starting point is going to be 1, because when you input 0, you're going to get 1 out. Okay. Oops, I don't think I was finished with it. Oh, maybe I was. Yep, I was. All right, you guys. So here it's talking about population as an exponential model. And what the book's trying to get at is that the way that it's looking from these numbers between 1950 and 2010, if you plotted them, it looks almost like a linear relationship, right? So it's talking about if it looks like a linear relationship, even though I know what's happening when there's a population growth is that it's exponential, it's going to walk you through the different ways to look at it. And I'll walk you through it now too. But I do want you to think about a family tree, because this is how population works, right? So you have your mom and dad, right? Your mom and dad. Or maybe you don't have both a mom and a dad, but however you came into this world, there were 2 people that had to make it happen, right? Regardless of how that happened, there's so many different ways, but biologically, there's 2 things needed. And interestingly, our population, if they only have 2 kids, right? Let's say they have a boy and a girl. If they only have 2 kids, our population would remain flat, because basically they are just replacing themselves when they die without adding any people to the population. Okay, so I just always thought this was interesting. You have to have at least 3 kids to show any sort of population growth. But how does that happen? Well, that happens when You have people who have more than that. There's people like me. I, at this point, probably will never have kids. So that's how you also get negative population growth, like it is happening in Japan, which is not great for the economy. But interesting side note, while we are talking about population growth, so what they did is they entered this data into your calculator, and I don't think they need you to do it. I can teach you later if you want, but they were able to have the calculator say, hey, what would be a linear relationship for this data, and what would a exponential relationship look like for this data? And they come down and the calculator says, okay, if it was linear, this is what the function would be. And if it was exponential, this is what the function would be. So here, what year did we start? 1950. Here it's saying, it uses a little bit of different numbers. Here it's saying our starting population for this function would have been 2.29 billion for the world's population. And here it's saying that starting population in 1950 would be 2.577. So you have a little bit of a difference there. And here it's saying the rate is, it's growing at 1.7%. And here it's saying that it's growing by 0.074 billion people per year. Okay, so that's the difference in those two functions. So which is going to best represent how population is growing? Interestingly enough, when they put in 51 years later, so what would that be, 2001 or 2000? So 2000 is 51 years after 1949. Okay, when they put in 51 into our linear relationship, their output is approximately 6.1 billion. When they put in 51 into our exponential relationship, they also get approximately 6.1 billion. So during that time period, during that 51 years, both the linear model and the exponential model worked, but we're looking at a very small piece of the graph, and you're not sure what's happening after that. So what they did was they went longer. They went farther past 51 years. So here they input 77 years into both. Okay, in the linear relationship, after 77 years from 1949, they get approximately 8 billion. And this would be what happens in 2026. Okay, and then here, if we put in 77 into the exponential function, we get approximately 9.4. And they're saying that the 9.4 is going to be closer to our world population in 2026. That's so many people, you guys. I can't even, so many people. So checkpoint 2 is just asking you to use these two models, the linear and the exponential, okay, to solve this problem. So the world population in 1970 was 3.7 billion. 2. Which function serves as a better model for this year? So you've got to figure out, remember our starting year was 1949. So how many years after 1949 is 1970? So go ahead and subtract that. You should get what, 21. So you are going to input 21 into both equations and figure out, how many of you guys just looked at your phone because my phone beeped? And figure out which output best matches 3.7 billion. By one projection, world population is expected to reach 9.3 billion by 2050. Which function serves as a better model for this projection? So you're going to do the same thing, but this time you're going to enter in 100 or 100, or 101, sorry, as your input, and try to find your output. Here, what it's talking about is just that a lot of times in the real world, instead of using different numbers as our multipliers, if we use the number e, which is irrational, like pi, which means the decimal goes on forever, which means you cannot find it on a number line because it literally goes on forever. So we know it's there somewhere on the number line. We know that e is in between 2 and 3 on a number line. But because it's not like we know 2.5 is right here, right? It's halfway in between. But 2.71828, we can't narrow it down enough because it goes on forever to actually find it on the number line. We can estimate where it is, but we can't find it. But this particular number works really well in a lot of real world functions. Okay. So here, all they want you to know is kind of, we're going to use E, and next chapter, we're really going to get into using E when we talk about interest. But right now, it gives us a function using E, and this one is for the concentration of alcohol in the blood. And it wants us to, gives us the equation, that's what it's talking about. In every state, it is illegal to drive with a blood alcohol concentration of 0.08 or greater. What is the risk of a car accident with a blood alcohol concentration of 0.08? So that's the risk equation. So when they input in 0.08 into this equation, which they show you how to do it on your calculator, I can show you too. Oh no, where did our calculator go? Did I close it from before? Oh no, here it is. We put in, it was 6 times E, and E is going to be blue, and then the second button, and then it's going to be the button right next to the 4, the natural log button. Okay, and then for the equation says 12.77 times X, but instead of X, we are going to put 0.08, the blood alcohol concentration. Okay. And our output is 16.67, right? Which is exactly what they got. So this means that your risk for being in a car accident with a blood alcohol rate of 0.08 is 16.7%. Using the same model to solve this problem, in many states, it is illegal for drivers under 21 years old to drive with a blood alcohol concentration of 0.01 or greater. What is the risk of a car accident with a blood alcohol concentration of 0.01? So just do the same thing that we did, except instead of 0.08, you're going to put 0.01. Okay, and I'm going to stop this one, and I will do a separate one for